In this video, we're going to define and discuss indexed sets. So if we are dealing with many sets at once, we often denote them with subscripts or indices. So like this. So we can use A1, A2, and A3, for example, instead of the sets A, B, and C. So if we do have these indexed sets, we can define the union and intersection over large numbers of sets and write it more succinctly. So the union can be given by the union from I equals 1 through n of AI, and then that's the union of A1, A2, etc., all the way up through AN. So that can also be written as the elements x, such that x is in the set AI for at least one I, where I is an integer between 1 and n. Similarly, the intersection of this set of n sets is A1 intersect A2 intersect ... through AN, which can also be written as the elements x, such that x is in AI for every I from 1 less than or equal to I less than or equal to n, where I is in the integers. So that's our definition. Just one thing to note in terms of notation, like both for intersection and for union. If we have something like this is where we start, this is where we end, and these are AI. So if we had this start and end point for AI, this would be the set of intersections. A3 intersected with A4, intersected with A5, intersected with A6, intersected with A7. So let's take a look at an example. Let's let B1 be the set containing 1, 3, 5, and 7, B2 be the set containing 5, 7, and 9, B3 and B4 be as written, and let's find these following unions and intersections. So find these sets. Pause and we'll talk about them together. Okay, so what is the union of these sets? So this would be B1 union B2 union B3 union B4. And if we want to write out its elements, anything that's in at least one of those sets is included. So from B1 we have 1, 3, 5, and 7. In B3 we also have the element 2, 3, 4 does not appear in any of these sets, but 5 does, 6 does, 7 does, 8 does, and 9 does. So that would be the union of those 4 sets. The intersection from I equals 1 to 4 of those sets would give us every element that's in every single one of those sets. So let's see. I see that 5 is in every set. So 5 is in the intersection of these sets. I see that 7 is in all of these sets. So 7 is in the intersection. Is there anything else in the intersection of all of those sets? It appears not to be the case. So that is the entire intersection. The intersection from I equals 3 to 4, now we're only interested in B3 intersected with B4. And so in that case, we see that 5 and 7, yes, those are in common between the two sets. Do we have anything else? Yes, 8 is also in common between those two sets. So 5, 7, and 8. Here's another example where AI is defined more generally. So the set AI is the set containing 2i, 2i plus 1, and 2i plus 2 for any i in the natural numbers. So I'd like you to find what is the set A3, and then what is the intersection from I equals 1 to 3 of the AIs. So again, pause and try this out. Okay, so what is the set A3? A3 is, we take the index I, and the first element of the set is 2 times that index. So 2 times 3 is 6. The next element in the set is 2 times 3 plus 1, so 7. Then 2 times 3 plus 2, so 8. So the set A sub 3 is the set containing 6, 7, and 8. How about the intersection of these sets? So A1 intersected with A2 intersected with A3. That would give us A1 is the set 2 times 1, 2, 3, and 4. Intersected with A2 is the set 2 times 2 is 4, 5, and 6. Intersected with A3, as we saw above, that's 6, 7, and 8. And we see that there are no elements in common with those three sets that are in each of those three sets. And so the intersection would then be the empty set. You may have noticed that this notation is similar to that of sigma notation for sums. So sigma, the Greek capital letter sigma means add up things of this type. And we start here, we end here, and we are adding up, in this case, things of the form I squared, so 1 squared plus 2 squared, etc. And if we did add those up, we would get 55. We can also do infinite sums, or you may have seen infinite sums, which are also called series. You may see this in, for example, Calc 3 or other courses. If you haven't seen them, don't worry about it. But for example, we could take the sum from I equals 0 to infinity of 1 over 2 to the I, and that is 1 over 2 to the 0, because we're starting with 0, plus 1 over 2 to the 1, plus etc., which is 1 plus a half, plus a fourth, plus an eighth, plus and on forever. And if you have encountered such things, you might know that this is a geometric series. So this particular one happens to converge to a finite number 2. Other infinite sums, of course, end up equaling infinity or things like that. But this is sort of a very nice one. Again, no worries if you haven't seen anything like that, but I just wanted to make the connection in notation. And similarly, we can take infinite unions and intersections of sets. Here is the notation for that. We could use I equals 1 to infinity of the set AI. And again, that would be A1 union A2 union A3 on and on forever. So that's also could be written as the set X, such that X is in the set AI for at least one I here in the natural numbers, because here we're going from I equal 1 to infinity, the set of natural numbers. Similarly, the intersection from I equals 1 to infinity is the set X, such that X is in AI for every I in the natural numbers. So above, we see that we're letting I range over the set of natural numbers. And this is an example of an index set. So I is the set of possible subscripts. So in our case, I is equal to the set of natural numbers. But this can change. We can have different index sets. Like in the previous example, I went from 0 to infinity, so it wasn't exactly the natural numbers. Here is another example below. We could let AI be equal to the set containing 0, 1, 2, 3, up through I, for I in the natural numbers unioned with 0. And with that definition, or with that notation for AI, I would like you to find the following unions and intersections of sets. So try this out on some paper, and we'll talk about it together in a moment. All right, so our set AI is the set of integers between 0 and I for each I in the natural numbers as well as I equals 0. So if we were looking at the union from I equals 3 to infinity of the AIs, then that would give us the set A3 would be 0, 1, 2, and 3. The set A4 is next, 0, 1, 2, 3, 4, etc. And we see that eventually we're going to get all natural numbers as well as 0, right? So this ends up just being the natural numbers unioned with 0, or in other words, the set 0, 1, 2, ... forever, all the positive integers together with 0. What if we take the intersection of those sets? So that would be A3 is 0, 1, 2, and 3. Intersected with A4 is 0, 1, 2, 3, and 4. Intersected with, and so on forever. What elements are in common with every one of those sets? Well, we see that 0, 1, 2, and 3 are in each of those sets. There's nothing else that's in common between the rest of those sets, every one of the rest of those sets. What about the intersection from I equals 0 to infinity? So that's a 0 intersected with a 1 intersected with ... So that's a0, all the positive integers from 0 up to 0, that's just 0 itself, intersected with 0, 1, intersected with ... That gives us just the set containing the single element 0. If we look at the union from I equals 2 to 5 of the AIs, so A2 union A3 union A4 union A5, that's going to be A2 is 0, 1, 2, A3 is 0, 1, 2, 3, and so on. Union with A5 is 0, 1, 2, 3, 4, and 5. And the union just requires that an element is in at least one of those sets. So we see that we will get 0, 1, 2, 3, 4, and 5 as the union of those sets. Finally, the intersection from I equals 2 to 5 of the AIs. So that's 0, 1, 2 is A2 intersected with 0, 1, 2, 3 intersected with ... intersected with 0, 1, 2, 3, 4, 5. And when we intersect those sets together, the only elements that are in each of those sets are 0, 1, and 2. As we saw above, the set I of possible subscripts is called an index set. It may even be the case that I is not a subset of the integers. So, for example, we could let the index set be the set of all real numbers R, or the index set be the set of all rational numbers Q. And in this case, we often use the Greek letter alpha instead of I for the elements of the index set, because I sort of indicates that we might be an integer. So if we look at this notation, we'd use alpha in the index set I. The union of A alphas is the set X such that X is in A alpha for at least one alpha, and again, the intersection X such that X is in A alpha for every A alpha. So this is the Greek letter alpha. So, for example, we could let A alpha be the set negative alpha to alpha for any alpha in the set of non-negative real numbers. So if that's the case, I'd like you to find A sub 2.3. What is that set? And then I'd like you to find the rest of those unions and intersections. Okay, so I could let, so what is A sub 2.3? That is just the open interval from negative 2.3 to positive 2.3. So that's an open interval from negative 2.3 to positive 2.3. Okay, what is the union of all the A alphas for any non-negative real number alpha? So what is this union? So we would include, say, for example, alpha sub A sub 2.3. We would also include, A sub 5 and so on. So if we union all things like that together, we get, the union of negative 2.3 comma 2.3 unioned with negative 5 comma positive 5 unioned with blah, blah, blah. I can't write these out in order. There are an uncountably infinite number of those sets. But if we union them together, what do we get? In this case, we get the set of all real numbers. Or, in other words, the open interval from negative infinity to positive infinity. Now let's look at the intersections of these A alpha for alpha in the open interval from 0 to infinity. So just to represent some things like this, we're talking about, let's say, A sub 3.2, negative 3.2 to positive 3.2, open. And what else have we got? We could have a sub some very small number, a sub 0.1, would go from negative 0.1 to positive 0.1, and so on. So if we're intersecting all of these kinds of sets together, we're saying what is going to be in common between all of these sets. So in other words, is there some x such that x is in A alpha for all alpha in the interval from 0 to infinity? So yes, there is. So one thing that's going to be in every single one of those sets is the point 0. So whatever alpha is, if alpha is in the interval from 0 to infinity, that means that alpha is greater than 0. So negative alpha to positive alpha contains the point 0. 0 is going to be in negative alpha to positive alpha for any alpha. And that means that 1 is in this intersection. Is anything else in this intersection? So nothing else will be in this intersection. If we let, say, x be greater than 0, then can we find some A alpha that x is not in? Yes. Then x is not an element, for example, of the set from negative x over 2 to positive x over 2. And that would be A sub x over 2, which and similarly for x less than 0, x is not going to be, for example, in the set x over 2 to negative x over 2, the opposite of x over 2, which would be the set A sub negative x alpha. A sub negative x over 2. So if x is not equal to 0, it's not going to be in at least one of these sets. Therefore, the only element that is in every single one of these sets is the element 0. So the intersection of these sets gives you the set containing only 0. Now for the union of the A alphas, where alpha is an element of the closed interval from 1 to 2. So A sub 2 would be one such set. So A sub 2 would go from positive to negative 2 to positive 2. A sub 1 would be another such set. But then there's all of these other sets in between. And what happens when we union all of those sets together? Well, we get any element that's in at least one of those sets. And because these are sort of nested intervals, it ends up being the case that this is the interval from negative 2 to positive 2 open, because this largest interval does not contain the endpoints. How about the intersection of those sets? So now we're just interested in what is in common between all of those intervals. And the open interval from negative 1 to positive 1 is a subset of each of those intervals. And so we do get negative 1 to positive 1 as the intersection of those sets, the only elements that are in every single one of those sets.